carries only one instrument, a wide field of view photometer telescope that simultaneously monitors the brightness of 170,000 stars with sufficient precision to detect Earth-sized planets in the habitable zone. Kepler must observe for several years to detect at least 3 transits of planets in the habitable zone to bring the signal level above the detection threshold and to validate the orbital period. A single large area of the sky is monitored to provide the large sample of stars required to derive statistical estimates. Note that most planets will not have their orbital plane aligned with Kepler's line of sight and therefore will not be detected. Operation in heliocentric orbit provides continuous observations 24 hours a day and about 365 days a year, which is needed to avoid missing transits. A large array of CCD detectors monitors 170,000 selected stars. The image below shows the highly curved focal surface covered with sapphire lenses that are used to focus the curved image on flat detectors. The small CCDs at the 4 corners of the focal surface guide the instrument to hold the star images on the same pixels for months at a time in order to avoid the noise introduced by uncontrolled image motions. The image at the upper right shows a Schmidt optical design that has a corrector element at the aperture and a large mirror that reflects the light under the detectors that are situated at prime focus. The low-level electronics that read out and digitize the signals are immediately behind. Because the Kepler mission observes 170,000 stars continuously, it obtains a substantial amount of astrophysical data. These data are useful to both the mission results and to stellar astrophysics. The left-hand panel shows the measured variability of solar-like stars relative to that of the Sun. The Sun is 3.6 billion years old and much younger than the galaxy. Consequently, it was expected that most solar-like stars would be older than the Sun and less variable. However, the Kepler results show that most stars are actually more variable. Thus, the measured signal-noise ratio of planets transiting solar-like stars was less than expected. This fact makes it more difficult to detect Earth-sized planets in the habitable zone of stars as large as the Sun. Certainly, Earth-sized planets were detected, but most of them orbit smaller stars or were in shorter period orbits. Another result of the mission is shown in the right-hand portion of the panel, i.e. the frequency spectra of acoustic oscillations of stars of varying age. At the top right are regular spectra of young stars burning hydrogen in their cores. In the middle are evolved stars that have expanded and are burning hydrogen in a shell. At the bottom are the red giant stars that are burning helium in their cores. As the stars evolve, the spectra move to lower frequencies and to larger amplitudes. Thus, analysis of this data provides the age of the stars and their planetary systems. It also provides the size of the stars and thereby the size of the planets, sometimes to an accuracy of 2%. This chart is a brief summary of the Kepler exoplanet detections. It plots the planet size versus orbital period for approximately 5,000 planets and planetary candidates detected by the Kepler mission. The large number of detections indicates that most stars have planets and provides the statistics needed for future missions. In summary, the chart indicates that many planets have short period orbits, most much shorter than our shortest period planet, Mercury, with its 88-day orbit. Most planets are larger than Earth, but smaller than Neptune, i.e. these planets are unlike any in our solar system. It is not known whether these planets are large rocky Earths or mini ice giants or water worlds. Although Jupiter is the size of a small star, Kepler found some planets that are even larger than it, but having too little mass to be stars. Because it's easier to detect large planets than small ones, the paucity of large planets with periods of less than 2 days is a puzzle. It is likely that a small number of detections seen in the lower right of the chart are an effect of the difficulty of detecting small planets when only a few transits are available because of long orbital periods. Jack Lissauer will now describe the wide range of scientific results derived from this data.
Thank you, Bill. As Bill showed in that last plot, Kepler found planets that are spread over a wide range of radius and orbital period. And indeed, it found for a wide class of planets and planetary systems. This plot shows the candidate exoplanets found by Kepler as they appear on the radius orbital period plane. The planets are represented by different types of points indicating the number of transiting planets that have been seen in the system in which they are present. And we see that almost 40% of them are in multi-planet systems with as many as 8 planets. We also see a huge range of diversity in the sizes and periods of the planets. There are extremely short period planets, although the abundance of planets goes up for periods of 10 days and more. And note here that there are substantial observational biases, geometric biases that limit the fraction of planets that transit to much smaller fractions for long period planets than for short period planets. And also there are biases in terms of the size of the signals that are needed. Small planets at long periods don't have many transits. They don't cause much of a drop in starlight, and therefore they're difficult to detect, which means that the paucity of planets in the lower right of this plot does not imply that planets in that region, which includes Earth, Venus, and Mars, are rare. So I'm now going to go and tell you more about individual planets and planetary systems. The first really exciting exoplanet discovery of the Kepler spacecraft was the Kepler 9 system that included the first pair of planets transiting the same star to be observed, and the first planets that exhibited clear transit timing variations. So nonlinear patterns of transits, not uniformly spaced. You can see here, in addition to an artist's conception of the system, on the top, there's a light curve with 2 sets of transits of similar but slightly different depth. zooming in on the light curves near the transits in the two bottom panels, you see light curves that are very similar in shape, but don't quite line up in the top. And those are lined up as well as they can be with constant times between the centers of transits. But if you allow the times to shift, because the planets perturb one another and change one another's orbits and move the curves relative to one another to get the best fit, you get these beautiful transit shapes shown in the lower part of these two panels. These timing variations between the two planets were anti-correlated. One planet was at that epoch gaining energy from the other, which was in turn losing orbital energy. And therefore the periods changed in opposite directions. The planets were on nearly 2-to-1 orbits. So one planet goes around the star about twice for every time the outer planet goes around. And this not only allowed us to confirm that they're planetary, that this is a planetary system, but also to measure the masses. In this case, it was combined with radial velocity. When more data were in hand, we were able to get much better estimates of the planet masses with just transit timing variations alone. Soon after Kepler 9 was discovered, the first rocky planet by Kepler was found. And this is an ultra-hot lava world with a period of only about 0.8 of a day. And because it orbited a fairly bright star, and its super Earth size about 50% larger in radius than Earth, we were able to measure its mass using radial velocity and show that the planet must be composed primarily of rocky materials, including iron. The next big discovery was the Kepler-11 six-planet system. It's a compact system of 6 planets, 5 of which have orbits that are significantly shorter in period than any planet in our solar system, and the outer planet is on an orbit that in our solar system would be in between the orbits of Mercury and Venus. All of these planets are significantly larger than Earth, the smallest being almost twice the radius of Earth, and the largest somewhat larger than Neptune. All are less massive than Neptune, but more massive than the Earth. Here we see on the left a portion of the light curve of the star Kepler-11 with the transits of each of the 6 planets marked with arrows of different colors. Note that near the right-hand side of that portion of the light curve, there's a very deep event, and that is the triple transit, 3 planets in front of the star at the same time, that is represented in the artistic rendition on the right. Depths depending on the size of the planet, course, periods on the orbital periods. The transits aligned as best they could for shape of the curves are shown on the left, and the transit timing variations are shown on the right. These are much smaller planets. They have smaller transit timing variations because they're less massive and perturbing one another by smaller amounts. It's more difficult to accurately measure their transit timing variations because their transits are less deep, but we still were able to measure them well enough that we could get mutual interactions among the inner 5 planets and get estimates of their masses without any radial velocity. So this was the first system where that was accomplished. And at the time, in 2011, these 5 planets were 5 of the smallest planets for which mass and radius had been measured.
The Kepler mission has found several Earth-sized and super-Earth-sized planets in the habitable zone of K and M-type stars. These stars are less massive and cooler than the Sun. G-type stars like the Sun were found to be too variable to provide sufficiently large transit signals needed for detection. The Kepler 62 planetary system consists of 5 planets orbiting a K-type star that is slightly less massive and cooler than our Sun, i.e. about 7/10 of a solar mass and about 900 degrees Kelvin cooler than our Sun. Consequently, the habitable zone, shown in green, is somewhat smaller than that shown for our solar system. 3 of the planets in the Kepler 62 system are interior to the habitable zone and therefore much too hot to be in the habitable zone. Kepler 62e is very close to the edge of the habitable zone. However, Kepler 62f is well placed in the habitable zone where water would be liquid on its surface. It is about 1.5 times the size of the Earth. Because no mass estimate for Kepler 62f is available, it is unknown whether it is a rocky planet like the Earth or a water world covered by an ocean. As an ocean planet, Kepler 62f would have an atmosphere of water vapor and likely also common gases such as carbon dioxide and nitrogen, similar to that of the early Earth. If the ocean is in contact with a rocky core, the ocean could have the components necessary for life. Unfortunately, determining whether Kepler 62f has life must await for the development of missions much more capable than a Discovery-class mission like Kepler. Kepler 186f is another planet in the habitable zone discovered by the Kepler mission. Again, several planets are found interior to the habitable zone. Kepler 186f is very close in size to that of the Earth. Its radius is only 21% larger than that of the Earth. Its mass and composition, however, are unknown. It orbits an M-dwarf type of star that has a mass about 1/2 that of the Sun and a temperature some 2,000 degrees cooler. This type of star has the highest average of the number of planets per star and is the most common type of star in our galaxy. The planets in the habitable zone must be physically close to the star to receive a heat flux sufficient to have liquid water on a planet's surface. However, the long period for the evolution of this type of star before it reaches the main sequence, and its frequent outbursts of energetic radiation could adversely affect the presence of life on these planets. Nevertheless, the multitude and propinquity of these stars will make them early targets in the search for life in our galaxy.
Now, this shows us some of the range of planets in terms of the physical properties, the mass and radius. Here we see with the colored points, the planets that were detected by Kepler and in both in its main mission and in its second phase known as K2. They represent a large number of planets, including many that are smaller than Neptune. The background grayscale here represents the total number of planets with precise mass and radius ranges in the given regions. And you can see that Kepler doesn't contribute a lot in terms of the fraction among the large planets that you see in the upper right, but it contributes a major fraction of the planets over on the left of this plot, which are the ones that are lowest mass. And many of these planets are surprisingly low density. Here I see some of the multi-planet systems found by Kepler. And this just shows their orbital periods within any given system. And it's an early view of the 3 and more planet systems. In our chapter, we show a more recent view that's restricted to systems with 5 and more planets. Moving on, we see in multi-planet systems what the period ratios of planets are. And we actually don't find very many systems that are in resonance, but there is an excess of systems just wide of these strong resonances between the mean motions of 2 planets. And there's a corresponding deficit of planets just a little bit narrow of these mean motion resonance. So there really isn't much of an excess in the vicinity of resonances, although there are few systems that have many planets, chains of planets in resonances. So this is an anomalous type, very interesting, but not representing the bulk of the planets. As you saw in the previous slide, exoplanets are really diverse, and they're indeed much more diverse than expected. This was indicated with the first exoplanets discovered, the hot Jupiters, but Kepler, with a much greater range of ability to find smaller planets, is able to show a wider diversity than had been found previously. And this is in all sorts of properties: radii, masses, densities, orbital periods, and even the albedos. And not only is there a great diversity in terms of the properties of individual planets, but exoplanetary systems also have a wide range of architectures. And in particular, flat systems, low inclination, like our solar system, are common among the type of planets that Kepler is best able to detect, which are short period planets. And also in this group, there are many closely spaced multis that couldn't be that much closer on their orbits, or the system would be dynamically unstable. Also, it's interesting that early in exoplanet science, most of the giant planets found, and that's what was being found in periods longer than a week or two, had large eccentricity. Well, it's found here that smaller planets tend to have lower eccentricities, and planets with observed transiting companions have lower eccentricity as well. One of the primary goals of the Kepler mission was to determine how common planets of given size and orbital period are among sun-like stars. This diagram presents results in the period radius plane with green regions showing the places where planets are most common, red showing where planets are rare, and gray where not enough planets were detected because either rareness or difficulty in finding planets of that size and period that we can get good estimates. Previous plot showed planetary occurrence rates as functions of the size and orbital period of the planet. The plot shown here on the left sums up the planets at various periods observed by Kepler and shows details as a function of planet size, revealing a valley depression in the number of planets with radii near around 1.7 times that of the Earth. And it's thought that most inner planets smaller than this are primarily rocky, and most larger have at least volumetrically significant atmospheres/envelopes. The plot here on the right shows that for small and mid-sized planets, these planets are more common around smaller stars, at least in periods of up to a few months, which are the ones really well explored by Kepler. Here we see an image of all of the Kepler planet candidates in front of their host stars. And planets and their host stars are shown at the same scale, and the colors indicate the stellar effective temperatures, the distances the planets are from the mid height of their star shows the distance they transited from the central transit. So Kepler lost two of its reaction wheels, and left with only two reaction wheels, it could not continue to efficiently point at its original field of view, which was off the plane of its orbit, so it could be observed year-round. Could only really observe well in the plane of its orbit, because then torques from the sun, the solar radiation, roughly canceled, so it didn't need as much to stabilize it. Therefore, could view just different fields and different ones at different times of the year. So this was an opportunity to explore a different part of. Here we see that K2 planets, that's what the mission became named after the first part of the mission, the original Kepler mission, ended. They're generally around stars that are closer and around stars that are brighter than Kepler planets. Now, Kepler ceased its observations almost a decade ago for the prime field, and then K2 observations stopped about 5.5 years ago. Nonetheless, those data are still in hand. They're available. People are studying them, and they are amazingly precise time series on close to 150,000 stars for a very long time. It's going to be many years before that precision and that duration light curves will be available for other stars. And therefore, even though there are newer things coming out, don't discount new science from the old data that Kepler obtained.
What have we learned from the Kepler results? Most stars have planets. Earth-sized planets are common. Planets of all sizes are found in the habitable zone. Planets unlike any in our solar system are common. Planets are found orbiting a wide range of stars, everything from neutron stars to giant stars to multiple star systems. Planetary systems have been forming since the beginning of our galaxy. Some implications of these results are: a new era in astronomy has opened. We now have large amounts of data available to study the structures of a huge variety of planets and planetary systems. And the Fermi paradox, are we alone, has become pertinent. Based on the fact that most stars have planets, and that some are Earth-sized and in the habitable zone, there are the order of 30 billion such planets in our galaxy. Yet SETI programs have searched for signals from exoplanet civilization with the world's most powerful radio telescopes and found none. What might explain this lack of signals? Some possibilities are: we haven't searched long enough with sufficiently sensitive equipment. Our assumption that life usually starts whenever the environmental conditions are suitable is wrong. It might be that the jump from organic material to life is an extremely rare event. It could be that life often starts, but evolution usually stops at the level of bacteria or single-celled organisms. Or that evolution stops with higher forms of life like apes or dinosaurs, but seldom develops technically proficient civilizations. A frightening possibility is that technical civilizations form, but are so unstable they always collapse. Kepler has answered its question: are Earth-sized planets common or rare in our galaxy? With new ground and space-based telescopes planned or in construction, we should be able to make progress on answering the next great question: is life common or rare in our galaxy?
Okay. All right, so thank you very much. So now it's a time for the discussion and the question. So so at the Zoom, or everybody's already ready to answer? So anybody who have, okay, yeah, over there.
Scott Wolk, Center for Astrophysics. Wonderful talk. My question had to do with the K2 data. There not only were they biased towards brighter stars, as you indicated, but they're also biased, or there's at least a large subselection of younger stars. And I was wondering if anyone had taken a look at the data and was able to identify whether the younger stars have different architectures than the systems around the older stars.
I don't know of any shown differences between the systems around the young stars or the old stars. It's quite difficult to do this type of comparison, in large part because the really substantially younger stars tend to be much more photometrically noisy. So it's much more difficult to detect planets around them. And if you're talking about differences between 5 billion and 10 billion year old stars, that you're not, there's much less likely to be substantial amount of evolution during that time than in the first few billion years.
Okay, see, over there.
Hi, this is Sarah Mulholland from MIT. Thank you so much for this review of this wonderful mission. So in terms of future science with the Kepler discoveries, I was wondering if you could comment on potential synergies with the Plato mission when it potentially revisits the Kepler field.
Bill, do you want to do that or you want me to?
I think you should do that, Jack. You've looked at that very carefully, and I think you've given them some suggestions to improve the mission expected output.
Okay, thank you, Bill. Very good question, Sarah. And I think it depends on how long they spend on the field and how many cameras they point at it. If they point such that Kepler is in their, this Kepler field is in their sweet spot, they'll be getting about half as many photons per unit time as Kepler did. They have more modern electronics, which is good. They have to combine light from 26 small telescopes, which will increase noise. So I don't know how those balance out, but certainly if they point at the Kepler field for a considerable amount of time, those data could be searched for together with Kepler and become the most powerful tool available to find the abundance of planets like Earth. So that would be very encouraging. We're hoping for that. Plato certainly will give some excellent transit times on many of the Kepler planets, and that will give some better mass estimates from transit timing variations. But the really exciting things about getting A to Earth better requires pointing for a considerable amount of time with a considerable fraction of their telescopes.
One of the most valuable things they can do, like Jack is talking about, is get transit timing variations of stars and planets that we've already found have them. And that gives you the mass of small planets. It's very, very difficult to get the mass of small planets in the habitable zone any other way. So even a few would be very valuable.
Thank you.
Okay, over there.
So hi, Bill and Jack. This is Tristan Guillot. I had a question about something we discussed earlier at the conference, and namely the tension between the RV survey frequencies and the Kepler ones. And it was shown that binary stars can account for these differences. And I was wondering whether you have looked at that specifically in the frequencies by studying the rate of binary stars that you have and things like that?
It hasn't been at the level that it could be. I think there could be more effort in this regard, especially now with all the Gaia data and Gaia, the ability with those data to assess probabilities of binarity for multi-star systems that are not resolved. So I think that's it's a good idea. It's a good research project. I don't know of it being done yet.
Thank you.
Yes, in the middle.
Hi, I'm Yasunori from ABC and Japan. So thank you for a great talk, the summary of the Kepler discoveries. I'm very curious about the PD ratio distribution of the pairs of planets from Kepler's. So I'm just wondering if there is a correlation between the radius ratio, the pairs for planets, and their PD ratio. For instance, so pairs of near-resonant planets are like the pairs in pot, or for example, pairs of non-agents planets have a large radius contrast. So do you have any information on the radius ratio for the pairs planets from the Keplers?
Yes, it's certainly that the closer, more nearby planets tend to have closer radii than more distant planets. And work led by Lauren Weiss and by Sarah Mulholland has shown that these correlations are more than can be explained simply by the selection effects of finding planets around stars with different noisiness and different brightness and similarities in period. But I'm not sure if there's really been quantitative work on how much similarity there is once you normalize for those very complicated selection effects. Maybe Sarah or Lauren would want to comment on this.
Okay, so first, Eiichiro, then back there.
Okay, hi, this is Eiichiro Kokubo. First of all, I'd like to thank the Kepler team for realizing this wonderful mission. And my question is the difference between K2 and Kepler planets. So Kepler focused on a small region of the sky, but K2 had a relatively wide kind of region, right, on the sky. And did you see any statistical difference between Kepler and K2 planets?
Well, Kepler observed this, had higher photometric precision, observed for much longer, and observed to much deeper to the fainter stars. K2 looked at brighter stars or smaller stars because there was more motion and therefore a much larger number of pixels had to be downloaded for each of the stars. So it's a search of a somewhat different region of parameter space. In a sense, K2 photometrically, characteristics of stars, amount of sky is something intermediate between what you get from Kepler and what you've gotten from TESS. So yeah, it's kind of halfway in between.
I see.
The other aspect, of course, is that K2, because it could look at so many different areas of the sky, could see a wider variety of stars and actually see some supernovas where stars were exploding and getting the information right from the start of that explosion. Kepler itself saw only about 2 supernova. Both systems gave good information on astroseismology, where you talk about the oscillations of the stars, giving you the size and age of the star. And of course, that's directly applicable to the information about the planets. So they were rather complementary phases of the Kepler lifetime. But as Jack has talked about, TESS, which is a successor mission, is giving us, again, a new aspect of the planetary systems.
And
Thank you.
the K2 fields were chosen in some respects to be complementary to the Kepler field and to include some clusters of young stars.
Okay, yeah, I understand. Thank you very much.
Okay, so final question.
Hi, I'm Yuki Ambara from University of Tokyo. My question, thank you for the comprehensive review of this wonderful mission. My question is about the mutual inclination of planets. So you mentioned that the flat multiplanetary systems are common. And is it possible to detect something from hidden, if there is a hidden planet with large mutual inclination?
I'm sorry, are you saying that you're asking about hidden planets, planets that we find because, for example, the timing variation of a particular planet that we're looking at indicates there's another planet, but that planet isn't oriented such that we see a transit. Is that what you're asking about?
Yes.
Yes, there are some planets that have been detected from transit timing variations. And in some cases, the perturbations are large enough, in a few cases, to get a 3-dimensional solution, and there are somewhat more inclined systems. I don't know if there's a really good statistical assessment. It seems like the closely spaced systems, which tend to have the largest interplanetary perturbations, tend to be relatively low inclination. There are some large perturbations for more eccentric systems, very few, but very interesting ones. I think it's Kepler 419 is one of these. And these can have much larger inclinations too. So it's not unknown that you have significant mutual inclination among planets, but it's very difficult to see, and it's not the most common thing, and it's certainly not common among the closely spaced planetary systems.
Nevertheless, some of them are seen, some of them where you see a planet almost certainly in the plane of the equator of the star, and another planet in the same system at a very high angle, maybe 90 degrees oriented, or maybe even more than that. So we can see, based on not only Kepler data, but some of the data from ground-based telescopes being synthesized to learn about these very strong inclinations and the kind of complicated interactions these planets undergo one with another. So one orbit will push another orbit to a different inclination. So there is such information, very, very interesting, helping us understand how planetary systems may evolve over time and move from planets that are in plane to planets where one or more planets is out of the equatorial plane of the star.
Thank you.
Okay, it's almost time. So please thank the speakers again. Okay, now we move on to the second speaker, Tristan Guillot.
Yes.